Okay.
The clicker?
Yeah, I do. So we're going to get started. We have about 40 minutes today to talk to you about all the things battery safety that we can condense about 20 years into 40 minutes. How many of you work in the battery industry or the STEM industry? How many are finance or investment? And then all the other people that help keep the world running. Awesome. Cool. So my name's Erika. I'm the founder of Electric Goddess. We started 7 years ago. We are a family-run bootstrap business. We basically design and validate batteries, mostly for space applications. Right now, we have over 200 satellites in space, which is weird. Unless they come down on your head, it wasn't us. And this is Luke. He's our chief scientist here at Electric Goddess. He's been here in the battery industry for over 20 years. You might know Zero Motorcycles or Joby Aviation, a lot of pretty extreme batteries that he has designed. Anything else you want to say about yourself?
I welcome engagement with questions at any time during my talk. Feel free to interrupt if the moment strikes you with a good question. I appreciate answering them because maybe somebody else in the audience has the same question. Also, I have a tendency to get fairly deep and technical. So if I'm losing you guys, you could say come back to less technical.
I would say about 50% of my job is being a Luke translator, so I will try my best here. At a high level, when you think about batteries, they store energy, and what you don't want is that energy being released in a way that's unplanned or unintended. There's been a lot of developments when it comes to cells and battery pack design over the past 10 years that I've been in batteries. But Luke is going to talk to you about where we see a lot of safety issues when it comes to cells, materials above that, and then also in the battery level. And so there's a few different applications you can look here too, and we wrote out the common failure methods we see because we also do forensics. So we get flown all over the world when a battery fails, and we figure out why and whose fault it was and how to fix it. And so you want to talk about some safety braking at materials first, Luke?
Sure. Obviously, the materials you select for your anode cathode are what most people talk about when they think of battery safety. Maybe they say, I use an LFP cathode, so I have, I believe we have X safety or whatever. But the reality about batteries is every cathode type can be dangerous. Every anode type can be dangerous, or they can be safe depending on how they're made. We've tested very sketchy, dangerous LFP cells that blow up in big fireballs, and we've tested cobalt oxide cells that had incredible safety behavior. Even though those aren't, of course, the standard rule of thumb you would go by with those chemistries, but underappreciated is not merely what is my cathode, what is my anode, but the electrolyte and even the additives package in the electrolyte has tremendous impacts on safety as well as durability and performance of that cell. I know there's probably some cell scientists here that already know this, but you could take the same dry electrode pack of say that we're doing an NCM cell with a graphite anode or whatever, and if we add just 20 parts per million of given organic additives, then suddenly the cell cycles like 2,000 times, and without those few ppm of additives, maybe it only cycles 500 times. And so this is one of the considerations where cell safety and longevity and performance can't be read by the datasheet parameters that it shows you. Like the datasheet might tell you, I've got an 811 NCM cathode, or I've got whatever, but that has a negligible effect on safety, durability, performance, because again, what your electrodes are based on is it's a factor, it's a factor, but it's one factor out of many dozens of factors, and it's not even the biggest player.
I think I would also just add on the material level, we put use case and abuse. So a big question we always get is how can you simulate 10 years in 3 months? And, with AI, there's a lot of things you can do, but really we rely on empirical data a lot because batteries surprise us all the time. So when there's new materials, there's things that you can infer and things that you can test, but also in batteries, a critical part of safety is also time, because things like separators crumbling, you may not actually know what to test for in early development, and you may not see it 3, 4, or 5 years down the road, and then there's a problem. So choosing materials is actually a very important thing when it comes to safety.
What she mentioned, separator crumbling there, that's a great example of a manganese dissolution problem. And as she mentioned, these can take years to form. So you can measure the mechanical properties and safety behavior of a separator and quantify it when the cell is new. And I've seen separators decay with manganese dissolution. Manganese ions do something called polymer chain crazing, which is where they'll actually depolymerize different materials like the polyethylene, polypropylene of our separators. This causes them to be, you can take a separator that was strong enough before that it was difficult to stretch or tear with your fingers, and after a few years in the presence of manganese ions, it can be so weak that with tweezers, lifting a piece of it causes its own mass to crumble and break under it. And this is a phenomena that occurs with any cathode type that may have manganese, whether that's NCM, manganese spinel. In my opinion, it's one of the reasons why a company like Tesla uses NCA cathodes. There's 1,000 papers that would show you why NCM has advantages over NCA, and yet they use NCA for the reason that NCA doesn't have manganese dissolution to wreck your polymers inside the cell, whereas others do. So that's an effect that takes years to detect that effect.
I just want to keep going because we're on a timer here. We can talk forever on batteries. At the cell level, there's production variability and performance decay. Performance decay kind of relates to those things we were talking about, which you can either see through testing or you can see it over time, the calendar cyclic. When it comes to production variability, even just the idea of licensing your cell technology to different factories across the globe, like there's going to be variability between each one of those factories. So how do you test that, right? You can do CT scans. That gives you a great glimpse into where the separator is inside of the cell. You can also open them up and do like tear downs. But there's definitely a lot of study that needs to be done within those production variability, whether there's different factories or even the same factory and maybe the team had a nice barbecue lunch that day, or maybe the team was, working 15 hours. Like that can make a big difference actually in cell safety.
Or something like the HVAC equipment that controls humidity in an area was under maintenance, and we've seen this lead to product recalls of everything that was manufactured during that period where it had abnormal humidity. And again, all of these phenomena are largely unrelated to the cell-based chemistry itself. We have. Has anybody heard of something called an arc or an arc calorimeter? Yeah, great. So in an arc calorimeter, it's a tool where
it's an accelerated rate calorimeter.
Yeah. So an arc is a tool to let you not just say, well, that one blew up and it looked pretty bad, and that one blew up and it looked less bad. An arc actually lets you quantify the total joules of energy released when a cell goes into thermal runaway. And our arcs also quantify gas pressure evolution rates, and we do gas sampling to determine what the thermal runaway byproduct gases are created. But by using this tool, you can quantify the safety behavior of a cell very precisely, down to what the thermal flux, power heat flux rate is at any moment, to how much total thermal energy was released. from a single 10 amp hour pouch, the record thermal value that we've peaked is over 40 megawatts of thermal heat power. So that's only for a few hundred millisecond duration before it is completed that reaction. But cells can have tremendous. You might think that their short circuit current or their electrical ratings are somehow related to their thermal runaway energy, but they're essentially unrelated. Thermal runaway energy is a one-time decomposition chemistry, sometimes involving the aluminum foil of the cathode is the fuel in a reaction that's a single replacement metal ion, oxygen reaction, just like thermite. How many of you guys made thermite with rust and aluminum dust as a kid? Probably did it for chemistry class. Yeah. So that same reaction where you take rusted iron and you cast boiling reduced steel as the byproduct, your cathode can do this same reaction. And what's interesting is it's unrelated to even needing lithium in there. So we'll actually take a cathode out of a cell. So it's nothing more than, say, some NCM material on an aluminum foil strip. And we'll wash this in an aqueous bath until we've delithiated this material. So there's no lithium left on this cathode. It is just mixed metal oxides bound to an aluminum foil with a PVDF binder. And this alone is all the ingredients you need for thermite to cast boiling nickel. If you can either just wad that cathode up, or you can put it in a coffee grinder and make a powder out of it. But that cathode will ignite and burn at temperatures over 2,800 Celsius, over nickel boiling temperature, because of that thermite reaction. So this is one phenomena that people like to blame the lithium in cells all the time, but in fact, you don't even require lithium being a part of the function to still make temperatures over 2,800 Celsius in the cell. So there's a lot of confusion over it being electrically related, and yes, often the electrical drive was part of what initiated it. Say you had a tiny foil edge tear or something that caused a short, then it was electrically induced, but don't confuse the electrical performance with the thermal runaway reaction once it kicks off, because it's it's drawing power from different mechanisms. It's enthalpy and it's heat releases from different kinetics than what you use when the cell's running electrically. Also important, if we were dealing with just say hydrogen and oxygen and we were burning those things, we would have a finite flame temperature that no matter how much hydrogen and oxygen we combined in our flame, and whatever pressure, how fast we jetted them together, we would never exceed the combustion temperature, which is limited by the specific heat capacity of that mass of gas times the joules of energy released when it undergoes combustion. And so you'll reach this plateau in upper temperatures, and you'll never exceed that plateau. In a battery system, there's no such upper plateau when you have faults in a battery system, for the reason that unlike a combustion temperature, where the material that's being raised in temperature is the material you're getting the energy from to raise it in temperature, this means you always have a finite ceiling. In a battery pack, you can have, say, 20 kilograms of cells over here, and your fault is some tiny 100 micron tear on the edge of a foil, and now you can dump the energy from 20 kilograms of cells all into a few milligrams of fault area, which means you can reach, plasma temperatures are in cell thermal runaways are easy to exceed 10,000 degrees, even 20, 30,000 degrees is possible. And so, of course, when you try to measure those temperatures, you're just rewarded by having a melted off thermocouple end. We use tungsten rhenium thermocouples. Are the highest melting temperature temp sensors in the world, and they only last sometimes 100 milliseconds before they're burned off and are open circuit. So the way you get data from that is spectral broadening. You have Doppler noise in the plasma emissions, and by watching what peaks are narrow, use a Fabry-Perrineau spectrometer to watch the spectral broadening, and that'll actually allow you to measure to temperatures that are tens of thousands of degrees, rather than being limited to thermocouple melting temperatures. I have the feeling I'm getting too technical, though, so we'll move forward.
It always comes back to spectrometers with Luke, so I appreciate that. I just wanted to kind of make a full circle, too, on the accelerated rate calorimeter that we brought up. Like, if you quantify the cell safety that helps you be able to plan your battery design. And I've seen incredible strides in cell safety, that it does come down to how are you putting those cells into a battery pack? How are you putting them into a system? And that's a lot of where we focus in the work that we're doing. And I just wanted to go a little bit, to be conscious of time here, on talking about design versus validation. We have this little spider chart here where we circled safety, right? Because you want to peg that out. But there's also a lot of other things that you have to trade off. And so you see this a lot in batteries, where you can't have everything. Like every lever you pull is changing some other lever to either be more or less.
Yeah, a classic trade-off in batteries is impedance or capacity, and there's never a moment with a cell that you can't choose to either give up impedance or choose to raise. But basically, if you can always trade one for the other, so that if you can tolerate lower energy density, then you can make a lower impedance cell, and if you can tolerate if you need a lower impedance cell, then you have to give up energy density. And so these are levers that you can pull the lever any way you want, but when you're pulling the lever in some direction, it's always pulling back from another direction. And this is sadly the case with safety in many metrics, in that cells that we test that have the most phenomenally exceptional electrochemical performance and insane energy densities, like over 450 watt hours per kilogram, and very high discharge rates and C rates, and even good electrical cycling stability. Normally the trade-off is that if they pulled those levers, then the safety lever was drawn back, from pulling those levers. So
and usually you try to mitigate that in the battery pack, and it's just, is it enough?
Yep. There's that question between if the cell, when we're doing calorimeter tests, if you pick a cell that has better electrical performance, but say it has 50% more total joules of energy released in thermal runaway, then you have to decide, can I tolerate this 50% more thermal runaway energy in a way that I don't end up worse off than if I'd just chosen a lower energy density cell that had better safety manners, right? So the classic example in cylindrical cells is some of the lowest electrical performance cells will actually pass propagation testing at spacing at 1 millimeter or sometimes less than 1 millimeter by a bit. And that allows your pack to be smaller and lighter. And cells that have outstanding electrical performance behavior may need, say, 3.5 millimeters, 4 millimeters for the same level of propagation resilience. And so this means that your overall pack ends up being bigger and larger by some extent. And so it's making that trade-off between balancing packaged safety of the system relative to cell level performance. And that's why just choosing the cell that's maxed out on electrical performance isn't necessarily going to give you a production battery pack that has maximum electrical performance, because assuming your production battery pack needs to meet propagation. Does anybody know what I mean when I say PPR testing by chance, or propagation testing? Okay, great. One person, that's good. So in a propagation test, it's the classic battery safety test for determining is my battery pack okay to ship or not okay to ship. This is probably the number one test used. And in this case, you preheat the battery pack to what would be a high but permitted operating condition. So say if your BMS turns off at 60 degrees Celsius or something, then you would preheat to like 58 Celsius, whatever it would still allow operations at. Then you would initiate a cell into thermal runaway in that battery pack at this, perhaps its full state of charge and preheated to just below max temperature. And then you validate, does that cell act like a firecracker chain and trigger the cell next to it? And does that cell trigger the cell next to that? And does the whole thing propagate? So when we say propagation, we mean, does one cell in thermal runaway spread to the next, spread to the next, spread to the next, so that the whole pack burns down in a giant fireball? Or does it, passing propagation would mean that you cessated that chain reaction event that you started, right? So you initiate a cell, and the pack is able to, like, we'll commonly use +6 as a passing criteria, so that if you initiate a cell and less than six further cells go into TR, then that's considered a thermal runaway pass. The reason for choosing 6 isn't arbitrary. It's because when you have a cluster of circles, they package with 7 circles with 1 in the middle. So you use that as your propagation cluster. So the propagation clusters need to be built with the same cell spacing, even the same cell spacer material as the real propagation. The real battery pack. We found an unexpected phenomena where we would use some outstanding thermal runaway mitigating potting, which has endothermic fillers and intumescent properties, so that it has an incredible ability to quench energy cell to cell. And it was still spreading. We were failing PPR, and we thought, why is this happening? So we were doing teardowns on them, and it turned out everywhere that the potting was had not propagated, but the cell spacer material that they were using was nowhere near as robust as the potting from thermal shock. And so we saw these little channels right through the cell spacer where it was plasma eroding right through the can wall everywhere that the cell spacer was touching. And so simply by removing that cell spacer plastic and going to an all potted system, turned that design that failed propagation to one that would pass with plus zeros, simply by eliminating the cell spacer from that assembly. So this is one of those situations where safety behavior changed drastically, yet the cell was the same cell they were using before, and the spacing was the same they were using before, simply eliminating that propagation pathway through the cell spacer in that case.
And batteries surprise us all the time, just kind of bringing it all together there. Like, we always get asked, how do you choose a cell? That's our number one question as battery consultants. And it's not a straightforward answer, because batteries surprise us all the time. Like, even the same manufacturer can change the recipe that they're using and not necessarily need to say anything to the end customer. So you're constantly testing. The data sheets are there as more of like a guide, but truly the empirical data is what's going to help you design a battery pack. And a lot of the testing that Luke's talking about is he just wants it to be safe. We always think about, if our parents were sleeping on top of their garage in a bonus room and they had a battery pack in their garage, what kind of battery would we want? And that's how we design batteries, is just super rugged also, and cost effective, because that's how people adopt them, right?
On that question Erika mentioned, of people ask us all the time, what cell should I be using for my product? The weird answer is that there's not actually just, I can't just tell you like, oh, use that one, because it's really kind of like horses, in that there's horses that are good at different things, and there's not one horse that's like, this is the best horse for doing everything, right? So if your application is a communication satellite, for example, which is what most of our work is today, then you're looking for something that has the ability to cycle, say, 30 to 60,000 times, because every 90 minutes it goes into the eclipse of the Earth and it runs on battery power. So you accrue massive amounts of cycles, and so you're looking for a cell, and maybe again in that communication satellite battery, maybe safety behavior matters, but matters less than if you were storing them in people's homes. When they're in space, if they have a problem, there's no humans around to get hurt by it. Obviously, we don't want to make space junk. And on that topic, all the batteries that we design for space have to meet demisability, which means they completely burn up to grain of sand size pieces when they re-enter in the atmosphere, so that you don't end up getting beamed by a battery while you're walking on the street someday. So those are all considerations where the battery that's right for that space satellite to serve internet around the world may be a great cell for that application, and it may be a terrible cell for your application. Maybe you're doing an electric bicycle here on Earth, or you're doing an aircraft battery, or whatever you happen to be designing a pack for. That same cell that's a great choice for someone might be the worst choice for you. And there's two things that are constantly tangling at a battery maker, at a cell maker. Having worked at a few cell makers now. It's this battle between cost and how good of a product you can make. And so R&D teams at And a cell maker will constantly be showing off that they can make exceptionally good performing cells if they use these exotic materials and these exotic processes. And then the cell maker team says, well, that's great, but we'll never do it because if it costs, even 5% more to make it, then it's off the table for most applications. Like this is one of the reasons why we try to stay out of automotive batteries in general now, even though I did them for years, is because it's not about what's good, it's about what's even 1% less money, and they'll do that at the fault of making like the entire product set they shipped to all be recalled in a few years, which Erika has a slide on
Luke,
the recall percentage. Well,
all right. I want to get back to validation gaps though on battery safety here. I love Luke's hot takes here. We talked a little bit about data sheets, cells are snowflakes at the end of the day, some edge cases that are under tested for battery safety, and maybe some production screening gaps that that you would like to see in the world.
Am I out of time for this slide?
No, we have one more slide, so
okay.
Let's do 2 minutes on
okay.
some validation gaps.
I guess your cell maker will give you a data sheet that just has the bare minimum that they need to have it be accepted as a data sheet, and most of those values will be lies, unless you're Panasonic or Toshiba, which are generally pretty honest. But for this reason, as someone say you're in your office and someone's asked you to choose a cell for a given application, data sheets would be like that rough ballpark that you may find them worth reading in some places, but testing that cell, particularly with its safety behavior, it's normal for a data sheet to have no mention of safety behavior other than say like it meets 38.3 shipping requirements or whatever. It was a pass without telling you any magnitude of severity or safety behavior information. So this factor is a bigger, like if you were to look at this spider plot for automotive, it would be 3/4 of the spider web is cost, and then they would fit all the other considerations off in the corner somewhere as things that would be nice to have. But when you're designing a cell or when you're choosing a cell for a given application, some of these may be really critically important to you. Some of them may not matter at all. And so that's something that I can't tell for you. That's up to your application and your individual needs, right? So as a scientist, I can quantify all of these things, but as a consumer of batteries, the customer of batteries buying the cells, choosing the cells, you have to decide which of these metrics are actually critical to your company working well, and which of them you can ignore. Because like Erika mentioned with the big lever thing, basically, if we can let say cost grow, or we can let impedance get higher, then we can always grow energy density, but C rate will drop, charge acceptance rate will drop. Something like self-discharge rate, this is really underappreciated because many, if not most of your aging mechanisms that occur in the cell are actually related to this self-discharge rate. So it's something that they never even write on a data sheet. I've never seen one once that mentions these values on a data sheet. But whether this value happens to be in the, say, tens or hundreds of nanoamp range, or whether this is in the microamp range, actually can make a massive difference in what your cell's aging like, for the reason that these are irreversible one-time chemical reactions, often that have gassing as a side reaction product. And so you only get, all cells only have a finite volume to fill with gases, right? So if this was just a resistor bleeding the cell down, we could just largely ignore it, and maybe it would be a nuisance that the cell's empty after a time. But it's no such luck. It's not an electron path. In fact, when we think about cell impedance, it's important to remember, like we write impedance here, but it's important to remember that the actual cell impedance of all the cells you've worked with is in the megaohms, because impedance is a measure of your electron path, right? what we call impedance in cells, and why when we load, we impose current on the cell and its voltage changes, and we measure that delta V to do V equals IR and call it impedance. It's actually not impedance. It's a multi-stage electrochemical process that gives us math that lets us use a value like ohms for it at the end of it. But in fact, the ohms value, the true ohmic impedance of the cell, better be in the mega ohms, or it would just self-discharge and gas out sitting there, right? So even the terms that they use on the data sheet are, it should technically say pseudo impedance. Like a long time ago, people called it, pseudo impedance and things, but people have just dropped all the prefixes like a losing formality sort of thing. But people have lost the meaning as well.
Thank you, Luke. All right, let's take a deep breath, everyone. Do you have to sit in a dark room to digest that? I might. Okay. Let's talk about the future outlook of battery safety. We talked about new materials, novel chemistries, and mechanical applications that are coming up. We really love the term rugged batteries. When Luke worked at Zero Motorcycles, he would put his batteries in crab pots and put them at the bottom of the bay here. Don't let the state hear that. But they were fine, and they came back up, and that was a good way to validate that batteries could live in the wild.
I do need to say it took a number of generations and iterations before I could pull them up a week later and have them fine from being on the bottom of the bay. But today they can meet that requirement just fine. It wasn't easy though.
So when it comes to better sensing, there was a great panel right before too, talking about a lot of the sensing that's happening. But really what we see with battery safety is that there's so many new materials, like what I said, that batteries are surprising me. So even cells that used to be super aggressive, now when we test them, they just don't care. Like I've actually had cells where we've like punctured them 6 times with a hot nail and they don't care, which didn't happen even years ago.
That's great. It's great to see that many of the tricks that improve cell safety, as I started this talk and I was saying, you can take any cathode chemistry and any anode chemistry and make a really safe cell out of it, or you can make a really dangerous cell out of it. So it's those tricks that, like just as one example, people do rather than a normal current collector foil, they will do a metallized PET film. So it's a polymer that they'll metallize a face on it. And why does that matter? Because that polymer actually shrinks and contracts when it's heated, so that you can do nail penetration testing on those cells all day, and they only get a degree or two above room temperature at the global cell level, because at the micro level, where that current collector was shorting against the nail, it was retracting hundreds of microns away from contraction, as it goes in, so it fixes its own short in real time. We have cells, that you can cut in half with a paper cutter, and they still have normal voltage even though they're leaking electrolyte out. And those are, there's multi-layer foil tricks you can do too. Something they do in high current pouch cells is they'll have say 6 foil layers instead of 1 foil layer to meet the cross section they need for their current collector. Why would they do that? They do it so that when you have shorting events, 6 times faster, basically, it's able to vaporize the local current collector around the impingement on the cell to fix that short. And these are all just examples that are, again, unrelated to cell chemistry. Those are mechanical, I don't know if you'd call it tricks or just good design, but it allows cells like Erika was mentioning, where we run them through really vigorous torture testing, and sometimes they only get a few degrees over ambient during those terrible tests, including everything from crushing them to cutting them in half to penetrating them, and some of the cells that we test today do nothing after all of that torture. It doesn't mean that they can't still burn, though. If a cell holds energy, if a device can hold a useful amount of energy, then that same device can burn down. We've got everything from supercaps to get them to blow up into fireballs to all the cell chemistries that people say can't burn. We've burned them all in our calorimeters, and if there's an energy storage mechanism, then that energy can be released in an unintended way. So there's no cell that is perfectly safe, but there are cells that you can use tricks to make getting that runaway to happen much trickier than other cells to induce into that thermal runaway mechanism.
So I guess what we'll leave you with before we take some questions is really, after all the years of designing batteries, testing many different ones, is that you need to test and validate early your safety. That's truly it.
Yeah, I let safety guide my cell selection these days. Electrical performance is what the client, of course, wants. And that's why they're putting a battery in their product, is for the electrical performance. But it's a smarter design ethos to build and design around safety first, and let the electrical performance that comes out of a safety design, be your performance needs, essentially.
The best battery is one you never have to think about once you ship it.
That's right.
All right, y'all. We have maybe time for one or two questions.
I love questions. You guys got some.
All right, friend.
So you mentioned all these trade-offs, and you can't trust the base chemistry. So when people try to go for like LFP, and they try to increase the energy density, closer to NMC, they add manganese, that you talked about. Are they inherently kind of trading off some of the safety of LFP to go towards the higher?
Well, they have one nice thing going for them in that that thermite reaction kinetic that I mentioned, where the aluminum is consumed as a fuel and steals the oxygen off the cathode. LFP is terrible at that. So in some regards, there's still some benefits to the base chemistry, but otherwise, you're right. As they jack up energy density, LFP cells get more and more violent. And if the trick they're using to jack the energy density of their LFP cell is adding a high fraction of silicon to their anode, then they start having thermal runaway that you would have a hard time telling apart from high nickel cathode cells, just because people almost always ignore the implications of the anode in thermal runaway. But in fact, the SEI that grows on the anode is almost always the weak link that triggers initiation for most all mechanisms. And it's also a huge factor in the total energy release of the cell. So basically cathodes take all the blame, and people only identify cells by their cathodes. But in fact, the anode and in particular the silicon fraction has a huge effect on safety. And yeah, as you drive towards more energy density, the thermal runaway behavior gets more and more ferocious.
Did we answer your question, friend? Okay, cool. Hey, Michaela. I think where all of our clients usually land is lot testing.
Yeah, we don't just run safety tests once. We take a benchmark set. So maybe when you're initially validating that cell, you run a very extensive set of safety tests, but then you'll take maybe 4 safety tests out of that safety test suite, and you'll run those on every new coming batch of cells, some lot. For the reason that, as we mentioned, the effects of even ppm level additive changes can have a big effect on safety. We've seen this. Even changing the ratio of something like FEC to DEC in electrolyte, you might think, what could 3 or 4% more or less FEC do? And the answer is like a doubling of thermal runaway energy is what we've measured from things like that. So
each like benchmarking tests or safety lot tests that you would do are based on the application as well. So there's not really a lot of blanket test plans that we make. It truly matters on what the whole system is and what it's going to do.
Yeah, tailored to the application, just like a good cell. What is a good cell? A good cell is a cell that works for your application, right? And the same thing with a test plan. We don't need to test a bunch of things that your application never has as a factor, but we sure want to make sure we don't forget any that we know it does have for a factor, right? So that's why we customize test plans to the application, because just like choosing cell selection is an application-based phenomenon.
Thank you all. Oh, wait, one more burning question.
We're buying like multiple different batches of cells, or we may go package design. I'm not sure. One of the things I was asking about is you can have a combination of destructive and non-destructive testing. With kind of when you're scaling up, can you use things like there's like about CT scanning to kind of look at where the foils are lying?
Oh, yeah.
But you're talking about different electrolyte, like electrolyte changes.
The-
How do you pick that up? Do you have to do mass spec on?
we do mass spec, and we do mass spec on thermal runaway byproducts. The for your application, I mean, can you tell us anything about your application, just so that we have a
Storage. So safety cycle life is like the key thing for us, not charging fast charging.
well, in that case, CT scan is really valuable for you because it's not just about say that you even scan just one cell, let's say, which a lot of people would say, well, that's worthless because it's not statistically relevant. But if you find in that one cell that the anode, I'm not going to do a cell design lecture here, but the anode must overhang the cathode by an aspect ratio that normalizes its electrostatic field potential from being at an edge. So basically, if you had an anode and cathode that were symmetrically lined up with each other, you would have something like a 50% electrostatic field concentration point at the edge of the electrode, which would cause non-uniform lithiation, and you'd have premature cell failure, even though it could pass QC. So this is a latent defect that goes through screening, passes QC, but can still, end in a fire for your program. And so CT scanning would let you quantify how much margin did they give for every one of those layers, and what does their tolerances look like with respect to how well could they maintain that margin, And if you see a cell where they are, let's say that they have 10 microns of precision and they've left themselves 100 microns of overhang in the design, then you could say, oh, well, it's pretty improbable that this will be a problem for me. But if you see a cell where they have, say, 50, 60 microns of winding stacking tolerance precision, and they've only designed in whatever, 75 microns of overhang, then you would say, this cell is only a numbers game away, even though you'd only scanned one cell, since you get to measure the overhang perimeter in thousands of places on that cell from one CT scan. You can quantify what does that tolerancing look like, and then there's some fairly simple math where you can extrapolate out whether, if I'm buying 10,000 of these cells, how many of them are likely to have inadequate anode overhang, right? So yeah, I love CT scans. We use them all the time. CT scans, no replacement for teardown, though, for the reason that polymeric aspects are vague because they have minimal X-ray cross-section attenuation. So works great for things like anode overhang, though, because all the metal parts in the cell and your active coatings are really well imaged by the CT. Yeah, UCT all the time.
I could go way deeper into that too. So we'll catch up with you later. Thank you, everyone. I really appreciate your time.
Thank you.